Welcome to Module 25, Alarm Engineering and Operator Response. In this module, we treat alarms as engineered decisions, not as automatic notifications from every point. An alarm is justified only when a defined person can take a defined action within a useful time. We will learn how to rationalize alarms by consequence, use persistence and state context, write messages that guide action, manage standing alarms, and measure whether the alarm system actually helps operators respond. The learning objectives are practical. You will separate alarms from events, assign priority by consequence, apply delay and deadband with state context, write useful messages, control routing and escalation, and use metrics to improve alarm quality. The important habit is to start with the required human response, then decide whether an alarm is justified. More alarms do not automatically create more awareness. When every point deviation becomes an alarm, operators learn to filter the noise. A professional alarm system is different. It exists to turn abnormal conditions into timely, accountable human action. That means every alarm needs a defined consequence, a defined response, a defined owner, and a way to verify that the condition was corrected. An alarm requires human awareness or action. An event records something useful, such as a mode change or equipment start. Status describes current condition. A maintenance notification may create planned work without interrupting operations. Analytics findings may support review. Classifying everything as an alarm overloads the operator and reduces trust. Alarm priority should reflect consequence and required response time. Consider safety, process impact, equipment damage, environmental consequence, redundancy, and the time available to act. Priority labels must connect to organizational response expectations. If critical and high alarms receive exactly the same routing and response, the distinction has little value. Conditioning the alarm is essential. Delay prevents transient conditions from alarming too soon. Deadband prevents repeated activation around the threshold. State context suppresses expected alarms when equipment is off, starting, defrosting, under test, or unavailable. But suppression must not hide persistent unresolved problems. The abnormal condition may still need to be recorded for evidence. A useful alarm message identifies location, equipment, condition, value or state, limit, consequence, and first response. AHU alarm is not enough. A better message says that a specific supply fan was commanded on but was not proven after a defined time, and that ventilation is unavailable. The message guides response without pretending to diagnose every possible root cause. Alarm engineering is a life cycle. It starts with philosophy, then identification, rationalization, implementation, operation, monitoring, and improvement. A rationalization review asks whether the alarm is necessary, its correct priority, condition, delay, message, response, routing, and owner. The life cycle continues after commissioning because building use, equipment, and operator practices change over time. The worked example defines a laboratory room high-temperature alarm. The condition is temperature above 78 degrees for 10 minutes. It is enabled in occupied or process active mode. It clears below 76 degrees. The priority is high based on risk review. The message guides the operator to verify airflow, cooling, and door condition. The route and escalation are defined. Routing should follow responsibility, schedule, area, and priority. Critical alarms may escalate when unacknowledged or unresolved, but routing too many alarms to email or mobile devices simply moves alarm fatigue outside the BES. Escalation should focus on alarms where action time matters and where the recipient has responsibility. Standing alarms and bad actors are valuable signals. Review the 10 most frequent alarms and the 10 longest standing alarms every month. This often reveals failed sensors, poor state logic, disabled equipment, training gaps, and deferred maintenance faster than a broad system review. The goal is correction, not simply lower counts. Useful alarm metrics include alarm rate, peak load, top bad actors, standing alarms, chattering alarms, response time, closure time, repeat rate, and alarms without defined response. Review metrics by system, time, mode, and consequence. The objective is not the lowest alarm count. The objective is timely recognition of abnormal conditions with manageable operator demand. Common mistakes include alarming every point deviation, assigning priority by equipment size, using delay to hide persistent failure, suppressing alarms without recording evidence, writing vague messages, equating acknowledgement with resolution, routing every alarm to every person, and failing to review standing and recurring alarms. Each mistake weakens operator trust. Let us summarize. Design alarms from human response backward to the condition. An alarm requires defined human action within a useful time. Events, status, maintenance notices, and analytics findings are not automatically alarms. Priority comes from consequence and response time. Delay, deadband, state context, and suppression must preserve evidence. Alarm metrics drive rationalization, defect correction, and lifecycle review.